Electrons, for example, can exist inside metals. And we've already kind of completely seen the phenomenon of polyparamagnetism. This we've already done about 3 lectures ago. And we're in the middle of Landau quantization. So we've done 2 lectures on Landau quantization. And today's probably our second last lecture on this topic. So, what I would like to do today is complete our discussion of the density of states in the presence of a magnetic field. Alright, so, and a quick recap is that if we consider 1D, 2D and 3D materials, so if this were our energy axis, and we are to plot the density of states in 3D or in 2D or in 1D, what would be the shape of this density of states? क्या shape होगी इसकी?
Inverse quadratic.
नहीं.
Quadratic.
नहीं. If you want to learn one thing from solid state physics, this is it. So you have free electrons inside a metal. You want to find the density of states. This will be the square root relationship.
Square root. Sorry.
What about this?
Constant.
Constant. This is no dependence on the energy.
Inverse square root.
This will be
Inverse square root.
minus 1 by 2. So the density of states is proportional to these powers of energy. So if I write G3D, this is some constant, C3D square E, G2D is some constant, no dependence on energy, and for a 1D chain, this is C1D E minus 1 by 2, right? And you should be able to derive what these constants are. These constants are important because when you integrate the density of states, you get the number density of electrons. When you multiply the density of states with the energy and integrate, you get the total energy. So it's very important to kind of once in your lifetimes calculate precisely what these constants are. If I were to write these constants for the 3 dimensions, they are 1 over pi square, 2m over h bar square, 3 by 2. Okay. This includes the spin factor. This is 2m over pi h bar square and this is 1 over pi h bar m over 2 1/2 e minus half. So these are the density of states, and when we place electrons inside a magnetic field, they go around in those cyclotron orbits. Landau quantization takes place, and the energy becomes quantized in the two-dimensional kx, ky plane. And the Landau quantization phenomenon, we've already studied that in somewhat detail. Homework number 5 will deal with Landau quantization. In short, the energy depends upon the quantum number L and the wave number kz. Magnetic field is applied along the kz direction, along the z direction, and the solid is it's a three-dimensional solid. So this energy is h bar omega c L plus half plus h bar square kz square over 2n plus if you had some magnetic field g mu b b s e. With these masses, so there's a mass in here and there's a mass in this omega c term, eb over m. So this is a component of the mass tensor. Parallel to the magnetic field, this is a component of the mass tensor, perpendicular to the magnetic field. And this, even though we're talking about electrons, but electrons inside the solid have some value of g which is different from 2. So this is, and then we also looked at the formation of the Landau tubes and how in the present you switch on a magnetic field, the nice three-dimensional grid collapses into those Landau tubes. And we kind of drew that nice tube inside a tube structure. Alright, so now what we would like to do, we would like to find out the density of states in the presence of a magnetic field. The density of states in the absence of a magnetic field for this solid is simply this density of states. Correct? Now, for a three-dimensional density of states, we would really like to do a convolution between a 2D density of states and a 1D density of states. Alright? So, if I were to kind of find out so there are two density of states that are involved. So one can imagine that if these were energies, this is an energy, let's call this energy E perpendicular, because it's in a plane perpendicular to the direction of the magnet. Let's call this energy E parallel. This energy is really small as compared to the other two terms, generally. So we kind of put that in the carpet for a minute. There are two kinds of energy, and these energies are totally independent. This kz value is totally independent of L. So if I were to draw this structure, if I were to plot versus kz, the energy as you know splits up into these parabolic curves. Each curve corresponds to a particular value of L. Kz is a variable that runs independently of L. And you can also have a constant kz, and L can take up values from 0 all the way up till infinity. Right? So these energies are independent. So the energy, the sum of this energy and this energy. And the structure in the K space for the states is independent, perpendicular to the magnetic field, than parallel to the magnetic field. So we really can take a convolution of a 2D density of states and a 1D density of states. So if I were to find out the density of states parallel to the magnetic field, this is due to this term. So this energy, this density of states is simply a one-dimensional density of states, which is given over here. It's C1d E minus half. So this is a 1D density of states. And in the two-dimensional plane, xy plane, in which the wave vectors kx and ky exist when you take the Fourier transform, the density of states, let's denote this by the parallel perpendicular, is given by the Landau-Thom structure. It's not given by this constant density of states, it's actually given by the Landau-Thom structure. So if you look at the Landau-Thom structure, we do notice that if you recall from our previous lectures, if I draw a Gaussian diagram, in the absence of a magnetic field, no field, all the energy levels up till EF are filled. But then I switch on a magnetic field here, I switch on a magnetic field perpendicular to the solid, to the one surface of the solid, and you get these splitting of this energy to equal space levels. This is the Fermi energy. So all the levels up to the Fermi energy are going to be occupied. Now the spacing between any two levels is h bar omega c. The lowest level is h bar omega c over 2. Each of these levels corresponds to a particular value of L. So now the energy level structure inside the two-dimensional plane has become quantized. If I were to find out write down the density of states corresponding to this structure, now this is my energy axis really, right? So on this axis, these are direct delta functions. So how can I write the density of states in this perpendicular direction? What kind of mathematical form can I write for this? I can write a sum of direct delta functions. Now where are those energies? So E minus, where are those energies? H bar omega c, L plus half. Right? Then you take the sum over what? L. Alright, so this is the density of states, but it's only approximate because each of these states has a certain degeneracy. Correct? Now the degeneracy of each state is 2 phi over phi naught. So many k points have coalesced onto each Landau level. So each of these drag delta functions has a certain amplitude. And we do know that the degeneracy was given if we include spin 2 phi over phi naught. This is 2 times b into the area, two-dimensional area, h e. Correct? So if I were to kind of find the density of states per unit area, then I wouldn't write this area term. So the density of states, which is really the amplitude of each one of these levels, is 2b e over h. Correct? I write an m here and an m here. I can do that. I can convert this to h bar, write a 2 pi here. This goes away. E b over m is omega c. So m omega c over pi h bar. Alright? So this is the amplitude of each of these terms. M omega c over phi h bar. So the strength of each of the drag delta function is just the degeneracy of that Landau level. Okay? क्या समझिए? वो कैसे आया? तो पूरा पूरा लेक्चर दिया उसमें रीजनरेसी वाला लेक्चर तो अपने आप उसमें जी so this is the number of states that coalesce into per unit area in an area A. So all the density of states that I have are per unit area, per unit volume, per unit length. That's why I divide by the area. Okay. Now I need to so this is in the presence of, now we're looking at how the density of states behaves in the presence of a magnetic field. So this is a kind of a scenario in which you have a density of states for free electron. You immerse the magnetic field and the density of states changes. So the energy band structure changes in the presence of a magnetic field. Okay, so this is a magnetic field induced band structure. The Fermi level also changes. So not only the density of state changes, the Fermi level also changes. Anyway, so if I want to find the overall three-dimensional density of states, what would I do? I have a 2D and a 1D and they are independent from one another. I don't multiply.
Convolution.
So 3D density of states. Now in the presence of a magnetic field, the function of E is going to be the convolution of these terms G Alright. So now let's write this down. Sorry? ये magnetic field हो जाएगा B. This is in the absence of a magnetic field. So now our definition for a convolution is that if I have two functions, f1 e prime, f2 minus e prime e ge. This is this function. So I take the first function as it is. I just, instead of e, write a dummy variable e prime. I take the second function, replace e with e prime but invert it and add a parameter e. And then I integrate over all e primes. When I integrate over all e primes, I get an answer that depends upon e. That's what this is. Geometrically, convolution has very nice meaning. So if I have a function of this kind, say this is one function, let's call this f1e, and I have another function f2 which can perhaps be a train of Dirac-Delta functions, a train of impulses. What I simply need to do, I could invert either of these functions. I can just choose any one function, invert it. So I take the mirror image of this with respect to the origin. Okay, so I kind of create f2 minus e prime. And then what this does, this is a slider. This is a slider. When e changes, so for any one value of e, so if I know what this function is, and if I add another parameter to the argument, it actually translates the function. Okay. So now what I'm doing is I'm translating this function. Move this around and multiply it with the other function. So now I take my function, which is inverted, and translate this across the second function. Now this is a train of impulses. It's zero everywhere. Only takes a non-zero value when it is at this point. So this function, I'm just sampling this function at different values of e. eventually, this is the multiplication process. So I invert, slide, multiply, and change my slider. That's what this convolution really means. So overall, the impact would be to replicate this function at the position of all of these Dirac deltas. So this is the result of the convolution. Okay? So if I have a three-dimensional lattice, I want to create this from a 2D and a 1D lattice, I take a 2D lattice and convolve it with a 1D lattice. If I have a 3D lattice and I have a pattern on each lattice point, which is called a motif, it's a collection of atoms, I take the convolution of that motif with the lattice, I can create the crystal structure. Okay? So all kinds of diffraction studies are based upon this idea of convolution. So now I want to do a convolution between these two functions that I generate the 3D density of states. Now, so the convolution, so now I write G 3D as a function of E in the presence of a magnetic field is simply the convolution between these terms. So C1D, I take, so I can spell out C1D at the very end. C1D M omega C over pi h bar sum over all L's. Now L goes from 0 to some number, LF. I'll explain what LF is. So it goes from 0 to some number, LF, and I need to multiply, need to find the convolution of this energy function and this Dirac delta function. Everything else is a constant. So I get integral dE prime. E prime goes from 0 to infinity. E prime minus h bar omega c L plus half multiplied by E minus 1. Okay? E prime raised to power minus half. So this is my convolution. Now this is really easy. Convolution with Dirac delta function is really easy because you can use the sampling theorem. And so if I spell this out, this becomes C1D M omega C pi h bar. L goes from 0 to some maximum number LF. So the integrand is a product of Dirac delta function and some function of energy, and you take the sum. Sampling theorem means that you only take those points of the second term in the product when the Dirac delta function is non-zero. And it's non-zero when E prime equals this. So I really need to find E prime must equal h bar omega c L plus half minus half. Good. So this is my three-dimensional density of states. Let me check. Oh, sorry. Bilguti. I'm so sorry. This is E minus E prime minus half. So this really is E minus E prime. Really is E minus h bar omega c L plus half minus 1. Okay? This is my 3D density states in the presence of magnetic field. So let me write this in a neater fashion. See if we 3D density of states in the presence of a magnetic field. I'll let the chalk बदल लेते हैं. C1d m omega c over pi h bar L goes from 0 to LF E minus, now this is non-zero when E prime equals this, E minus h bar omega c L plus half minus 1, okay? So this is my three-dimensional density of states. So good, so nice. Now what is this LF? Now the Landau levels go from 0 to infinity. They are quantum numbers that can range from 0 to infinity. But there is a Fermi level, which tells you what's the maximum energy for the electrons. So now what we would like to do, not all those levels are filled. You really want to sum up only up to those levels, such that the maximum value of L, which is LF, is less than the
Fermi level.
the energy. So you want your LF is LF really is the maximum L such that h bar omega c L plus half is less than or equal to EF in the presence of a magnetic field. So not all the levels or not all the L's are fixed, so it's a finite series. So this is how we define L. Now, if I were to plot this, it's nice to see what the plot looks like. Any guess what it might look like? In order to draw these plots, it's easier to do a little bit of change of variables. ये क्वेश्चन समझ आ रहा है कि अब हमें डेंसिटी ऑफ स्टेट्स निकाली. एक चीज हमें समझ आ रही है कि in a 3D solid, in the present absence of a magnetic field, the density of states is a kind of nice continuous curve. It's an analytic curve, square root function, and it truncates at EF. So this goes all the way up to EF. Then it drops to 0. That's how we define EF. This function, however, is not a nice function, because if you observe that when E at certain precise values of energy, which equal to the Landau energy levels, this figure kind of blows up, because the 1 over half is in with minus sign, so it's really in the denominator. When E equals h bar omega c L plus half, this number becomes very large. So it kind of peaks. The density of states peaks. We really like to plot these functions. ठीक है, हम plot करना चाहते हैं. उसके थोड़ी सी आसानी हो जाएगी if we make slight change of variables. But in order to do that, we need to find this factor C1d m omega c. Remember, by the way, that which of these terms has the B dependence in it?
Omega C.
Hmm?
Omega C.
So this has a field dependence and this has a field dependence. This represents the values at which the energy peaks and represents the spacing between those peaks. So not only the spacing changes, but the strength of each peak also changes. It also depends upon the gravity. Because the spacing changes, the peaks dilate, which means they kind of breathe out, they become further apart. Fewer peaks will fit within the Fermi level. Therefore, the number of electrons that go onto each Fermi level, each Landau level, must go up, so that the total density of states remains the same. Because particles are not being created or destroyed here. So, in order to kind of plot these in some mathematical toolbox, like to do a change of variables, we should also like to find out what this term really is. So if I look at C3D, and if you do these calculations, you'll notice that it takes few directional points. If I take at 0 kelvins a 3-dimensional 3D density of states, no magnetic fields over, no magnetic fields. If I take GE 3D function of energy and I integrate with respect to energy from 0 to EF, what should I get? GLE में ऐसे सॉल्व करते हैं, क्या होता है गेम में? Density of states is the number of states per unit volume, per unit energy, and you're integrating over energy. So what does this represent at 0 kelvins? Total number of electrons. Okay? Total number of electrons per unit volume m. So from here I can find a relationship between n and EF. So you just take that G3D over there, put this in here, you integrate. It's easy to integrate because this is square root of under root E. You get an EF in your answer. So this gives you a relationship between EF and N. EF depends upon the number density at 0 kelvins. So if you were to do this calculation, this is probably a homework problem. N is 2 by 3 G3D EF. Or G3D EF. The density of states at the Fermi level is 3 by 2 N EF. Alright, and you can verify this. If I put this value in here, 3 over 2 NEF, and square root E and integrate, I get M. So this is a relationship between G3D EF and EF and N. H bar omega C. I normalize with respect to H bar omega C, a new variable x. And then I also define x naught, which is the normalized Fermi energy. So these are the two kind of substitutions I would like to make. So my G3D EF is G3DE. If I'm interested in finding G3DE, which is over here, this term over here, this term will also depend upon GEF. Alright. So if I just insert this term in here, I can find the relationship between G3D and that coefficient. Overall, the result would be G3DEF X over X naught. Now, in the absence of magnetic field, चलिए करके दिखा देता हूँ ताकि आपकी तसल्ली हो जाए. Pi square 2m over h bar square 3 by 2 under root e integrate dE. This should give me n. Correct? So this is 1 over pi square 2m over h bar square 3 by 2 e 3 by 2 3 by 2 right. This gives me 2 by 3 pi square 2m over h bar square 3 by 2 EF 3 by 2. This must equal m. This must equal m. Alright, so what this does, this gives me the relationship between EF and N. Equals h bar square over 2m n 2 by 3. Now my so what do I need to do is this is a relationship between EF and N. अच्छा अब हम करना क्या चाह रहे हैं अब हम ये चीज ड्राइव करना चाह रहे हैं G3DE is this thing
And यहाँ पे feedback over to the in EF.
Yeah, it's a algebra and it's so EF is n 2 by 3 step by step. EF 3 by 2 is n 3 pi square over 2 h bar square over 2m 3 by 2, correct?
Yes, sir.
So now I kind of take the power with 2 raised to power 3. This becomes n 2 by 3 h bar square over 2m pi square. Oh yeah, into 2 by 3 3 over 2 2 by 3. अरे क्या हो गया? अच्छा जरा खुद से ड्राइव करें ना, ये जरा ड्राइव करें, प्लीज ड्राइव दिस. M, we know this. So C3D, so this means that C3D, this is E 3 by 2, 2 by 3. This must equal N with an EF, right? What this means is that C3D equals 3 over 2 n EF 3 by 2. Correct? Now this also means that C3D from this relationship we what we are interested now is we want to eliminate n, so n is 2 over 3 G3DEF into EF. This is our n. 2 over 3 G3, this is our n, so we just put this 3 over 2 EF 3 by 2, n is replaced by 2 over 3 G3D EF with an EF. Correct? So now what this does is I can get rid of these terms and I'm left with square root EF in the denominator. Finally, what this means is C3D is really equal to G3D at EF divided by square root of EF. What this also means is that my G3D at zero field, I'm always at zero field right now, for any energy E is G3D EF 1 over root EF E square root, correct? So this is E over EF square root. E over EF square root in our substitution. E over EF is x over x naught square root. So this holds true. Okay. So now one of our relationships, this has really become a function of x. I have recast E in terms of x, which is just a renormalized energy. So in the absence of a magnetic field, G 3 x over x naught square root. Now in the presence of a magnetic field, what we would like to do is, we would like to express this in terms of x, then it becomes easier to plot. So if I were to express this in terms of x, I can write G 3D, function of E. Now in the presence of a magnetic field, C1D, what is my C1D? It's that term over here, 1 over pi h bar m over 2 1/2, alright, m omega c pi h bar, correct? L from 0 to infinity, correct? And then I could take E over, so now if I were to find E, if I were to take h bar omega c, so what I could do now is I could really write h bar omega c minus half E over h bar omega c minus L plus half right. So just take this h bar omega c minus half as common. Now this h bar omega c minus half, this just comes out. So I'm going to 1 over pi square h bar square m over 2 1/2 m omega c. Let's write this as h bar omega c square. L 0 to infinity. Now this is, I define this to be x minus L plus half I can do some manipulations here. This is really h bar square, this is h cube over 2, this is an m here, this becomes omega c in the denominator. So this becomes 1 over pi square h bar 2 bar square so if I insert an h bar here, I can put an h cube here, and this becomes h cube m over 2 1/2 m h bar omega c square. L 0 to infinity x minus L plus half minus half. Okay. Now, if you notice that you will notice that EF is hidden somewhere here. EF is going to be hidden somewhere here, and actually AHQ. So from here you can actually find out a relationship between E. Okay. So there's an EF over here in the denominator. So I can explicitly show you that. Right? So if I take this expression and bring it here, this is my C3D. This is G3D EF at EF 1 over EF square root. So this is my C3D with square root E. What this means is that all of this thing must equal this. Correct? What this means is 1 over pi square 2m h bar square 3 by 2 must equal G3D EF over square root F EF. Now if I look at this term over here, let's kind of write this term over here. Let's write this here. This is numerator has m 3 by 2 h cube which is m over h bar square. So I've taken care of this, taken care of this, taken care of this. 1 over pi square. So this term have been taken care of. There's a 1 over under 2 left over. So there's a 1 over under 2 left over. The rest is G3D EF square root EF h bar omega c over sum of L's. All of this. ठीक है? A factor of 2. So there's really a factor of 2 in the denominator. Okay? So this is my expression. Finally, what this shows is that my three-dimensional magnetic field density of states is given by G3D EF factor of 1/2. Alright. And then this EF over h bar omega c is x naught square. So I get another 1 over x naught square root. Sum over L's goes from 0 to L f x minus L plus half minus half. Let's try to plot these density of states. ठीक है? at zero field is given by this thing. So let me plot this. Instead of plotting G3D as a function of x, let me plot G3D divided by G3D at EF over square root x naught. This will be square root of x naught x. Okay, so this is some constant, the density of states at the Fermi energy. X naught is EF over h bar omega c. This is also some constant for a given magnetic field. Okay, and then what I could also do is so I fix the magnetic field. B is fixed. So h bar omega c is fixed. Now I see what is the density of state, which is a function of energy. Right? So I fix B. So I can only make these plots when I fix B, because fixing B fixes h bar omega c. Because there's an h bar omega c here and h bar omega c here. I fix that. And I just want to find out how does this change with x, which is the renormalized energy. Likewise, I want to plot this thing. G3D as a function of x. You can always switch back from x to E and vice versa. At some magnetic field. Now I also normalize this by the same variables so that I can make a comparison. Okay? This is 1/2 L goes from 0 to some number LF. Now let me write this in this to the third form, x minus L plus half. Right? So these are the two density of states I wish to plot and compare. Got it? ताकि आसानी से मैं प्लॉट कर सकूं किसी सॉफ्टवेयर में. With respect to the density of states at the Fermi energy. Dimensionless. G is also dimensionless. So let me try to plot these and see what they look like. L is 1, then x has to start from 3/2. Okay, because of this thing. So you have this minimum energy here is h bar omega c over 2. So I think that is the reason why we are not getting real numbers over here. So I'll figure this out and let you know. In any case, what we need to do next, give me 2 more minutes, is square root. It goes up as a square root. This energy is going to be peaks separated depending upon the value of L. So there's going to be, for L equals 0, there is going to be a peak at x equals 1/2. For L equals 1, there is going to be a peak at x equals 3/2. Alright? And that's the lowest value of x from where we need to start counting. So if I kind of break this up into pieces, half, 3/2, 5/2, 7/2, and so on, there's going to be a peak over here. There's going to be a peak over here, a peak over here, a peak over here. And if I were to plot this, the density of states is going to look like this. This is what the density of states will appear like. This fall off is a 1 over square root fall off, and then you get another peak at the next value of L. So now what this really shows us is that if you have a magnetic field, there are states only at precise values of x. Remember that x is E over h bar omega c. only at precise values of energy will the states exist. The density of states becomes quantized. This is the Landau quantization. The Fermi level will exist somewhere, right? This is the value of x naught on this dimensionless scale. So a number of peaks will lie at x less than x naught, and all the electrons will be populated onto this density of states. Okay, so now we need, if you would like to find out the total number density, you just take the density of states for a given magnetic field. This graph is at a given magnetic field. If I change the magnetic field, what's going to happen is that this density of states is going to change. This Fermi level will slightly shift as well, but the separation between two peaks is going to dilate. As a result, there will be fewer number of Landau levels at energies below the Fermi energy. So you want to count the total number of electrons, you just integrate this density of states. If you want to find the total energy of electrons, you multiply this density of states, take this everything back to the right hand side, multiply this with energy and integrate. Now a useful quantity is called the integrated density of states. So what I could do, I could take these density of states and integrate them with respect to x. Okay, so if I integrate them with respect to x, I'll get the integrated density of states. This integration is really easy because it's an x 1 by 2. This integration is also easy, but you really need to take into account what should be the lower value of x. And we're going to continue with this discussion on Thursday and wrap it up. And the real point is that this quantization of the density of states results in oscillatory phenomena. You see, the density of states at the Fermi level at x naught could be anything. It depends upon how big the magnetic field is. When you change the magnetic field, it might appear that a peak traverses this Fermi level. And when a peak traverses this Fermi level, you get a spike in the conductivity. The magnetization will also become oscillatory. So the magnetization shows oscillations as you change the magnetic field. Some point is high, at some point is low. The heat capacity will also show these oscillations. These singularities here at precise values of x, they are called Van Hove singularities. So in the next lecture, what we would like to do, first of all, I would like to kind of show you how to plot these properly, and then I would like to show you how this results in different oscillation and different physical properties of the materials, different kinds of materials. Okay, so please do the algebra yourself. Yes, please. ये singularity कि जब x equals this to get a peak, that's called a singularity. अच्छा, अब आपके projects जो हैं